Hi, this is Johnny with Simpson Math. Today we will be covering the double angle identities. I hate to just write them down and say memorize them and show you how to use them. So I'm going to start off today with showing you like the derivation process. We're going to try to come up with these identities to help you memorize them and get more comfortable with them. And we're going to do that using our old sum and difference identities. So let's start off, let's derive sine's double angle identity. And in order to do that, like I said, I'm going to use sine's sum identity. I'll just start off with something we already know, the sine-sum identity. If I have sine of the sum of two angles like alpha and beta, that's equal to sine of the first angle times cosine of the second plus cosine of the first angle times sine of the second angle. That's just the sine-sum ID. Now, I'd like to use this to come up with the sine double angle. So what I really want is for this sum to be double some angle. So maybe this is, I don't know, 10 and 20. So 10 and 20 will add up to 30, and I want to think of 30 as being double some angle, like 15 degrees. So I'm going to pretend that A and B are the same. In fact, let's let alpha equal beta. Let's let them equal to each other. And in fact, I'm going to call it a different angle altogether. I'm going to call it x. So I'm going to go through and I'm going to replace all of my alphas and betas with the x variable. So instead of alpha plus beta, I have x plus x. Then I have sine of x times cosine of x plus cosine of x times sine of x. On the left-hand side of my equation, I've got sine of x plus x. Well, this is just two x's being added together. So I have the sine double angle, sine of 2x. And on the right-hand side, these are the same term. Multiplication is commutative, so cosine times sine is the same thing as sine times cosine. So I have one of these plus another one of these. Together, I've got two of those. This is sine's double angle. That's the first one I have written on the board up here. Sine of 2x can be rewritten as 2 sine x cosine x. I'd like to do the same for cosine. I'd like to derive cosine's double angle. Similarly, I'm going to start off with the cosine sum identity. So, hopefully you have this memorized by now. If you have cosine of alpha plus beta, that is, I'm taking the cosine, or evaluating cosine, of two angles being added together. The cosine sum is cosine of the first angle times cosine of the second angle minus sine of the first, sine of the second. Well, I would like to see what happens when these two angles are the same measure. So I'm going to let alpha equal beta, and in fact, I'm going to call it something else. I'll call it x. So I'm going to go through and replace all my alphas and betas with x's. So I have cosine of x plus x equaling cosine x times cosine x minus sine of x times sine of x. And those two, well, if you take cosine x times cosine x, you get cosine squared x. So I'm just going to clean this up. X plus x is 2x, or cosine's double angle. And this is equal to cosine squared minus sine squared. If I were to add cosine squared and sine squared, we know that would sum to 1. But if I take sine squared away from cosine squared, that's equivalent to the cosine double angle. Now, this pops up a lot in problems that we're about to do, in verifications and in evaluating. In fact, there are 3 variations of the cosine double angle. So if you can just memorize this one, that's great, as long as you then know how to derive the other 2. So let's say you've got cosine squared minus sine squared, but for maybe you only want to be dealing with sines. So if you're verifying an identity on the other side of the equation, it has sine, 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 then maybe what you want to do is rewrite this side of the equation in terms of sine. Well, I can do that using a Pythagorean identity. I'm going to go off to the side and just play around a little bit. OTS off to the side. I know sine squared and cosine squared are related to the Pythagorean identity where sine squared x plus cosine squared x equals 1. But if I want to take cosine squared and replace it, then that means I want to take this equation and solve for cosine. So I'm going to subtract sine squared from both sides of this equation. I subtract sine and subtract sine. That leaves me with cosine squared x equals 1 minus sine squared x. I'm going to make that substitution in this step right here. Again, this is just me rewriting cosine in terms of sine. In this format, I can see, oh, the sine squares are the same term. In fact, they'll add together. -1 plus a -1, I've got -2 of those. So cosine's double angle is also equal to or equivalent to or can be rewritten as 1 minus 2 sine squared of x. All right, I could do this very similarly where I take the cosine squared minus sine squared and replace the sines with cosines. Let's do that. So I'm starting with the cosine double angle, which is cosine squared minus sine squared x. Cosine double angle identity. And this time I want to take my sine squared and replace it with what it's equivalent to in terms of cosine. Sine squared can be rewritten as 1 minus 2, no, that's not right, 1 minus cosine squared. Ooh, now parentheses are very important here. If I take sine squared and I replace it with a binomial, I am subtracting both of these terms. So like before, I'm replacing sine squared with 1 minus cosine squared. I'll have to subtract both of those terms though. So I have cosine minus a negative cosine. That's actually going to add together and become 2, positive 2 cosine squared minus 1. So cosine's double angle, if you ever see cosine 2x, you can replace it with 2 cosine squared x minus 1. So on the board I have written down the 3 variations of the cosine double angle. Cosine double angle is the difference of cosine squared minus sine squared. It's also the difference of 1 and 2 sine squared x. And it's the difference of 2 cosine squared and 1. These 3 variations we need to be comfortable with. We need to be, when we see one of these, we should recognize the cosine's double angle, and we should be comfortable rewriting cosine's double angle as either one of these 3. All right, the tangent double angle is very similar. I'm going to leave that as an exercise for y'all to do on your own, but I can almost see it. Tangent's sum is tangent plus tangent over 1 minus their product. So I can almost see it. I think you can do it on your own. Try to derive the tangent double angle identity coming straight from the tangent sum identity. All right, so there they are. We've got the identities. Hopefully we've got them written down so you can look at them while we now use them on a couple of examples. So let's see something that may come up. Oh yeah, maybe I want to find some exact values. So something similar to this. If I take 2 times tangent of 75 degrees divided by 1 minus tangent squared 75 degrees. What is that equal to? You may be thinking 75 degrees is at 5 pi 12ths. Maybe we talked about this last time where we could maybe use a sum and difference to figure that out, but that would just be step one of a multi-step problem. I think there's maybe a faster way to approach this. So I'm just going to look again at this scenario. I've got 2 times tangent of some angle over 1 minus tangent squared of that same angle. If I've seen that before, oh, look at that. Yep. If this x were just 75 degrees, I could take this and rewrite it as double that angle. So this is just the right-hand side of the tangent double angle. So that means I can rewrite this as tangents double angle. If I have 2 times 75, I can rewrite it as such. If I have this, I can rewrite it as such. Okay, now I think I could do this. 2 times 75 degrees is just tangent of 150 degrees. 150 degrees is on our unit circle. If I'm just mentally, I think it's the closest tick mark to 180 degrees. And I've got tangent memorized there as the square root of 3 over 3, negative because I'm in quadrant 2. Bam. So I think I called these last time the fun problems, or just they're quick and easy as long as you know your identities. Let's do another example of something like that. How about I throw in a radian? So this example, I want to find the exact value of 2 times cosine squared of negative pi 8ths minus 1. So I'm hoping you recognize this third variation of the cosine double angle. I've got twice cosine squared some angle minus 1, meaning I can rewrite it as cosine double that angle. So this is just equal to a single cosine of double negative pi 8ths. Notice that 2 on the outside kind of goes away, and then minus 1 is no longer there. This is just cosine double angle. I can double negative pi 8ths. That becomes negative pi 4ths after the reduction. On the unit circle, this is negative 45 degrees. And there I know the cosine should be positive because my x values are positive in quadrants 1 and 4, and that's that root 2 over 2. Just a side note, something we talked about last time or previously were even and odd identities. As soon as you get down to a cosine of a negative angle, that's an even function, so the minus sign can just be almost ignored. So cosine of negative pi 4ths is the same thing as cosine of a positive pi 4ths. It still has that x value of positive root 2 over 2. All right. Also, because they're identities, of course I can give you some new verifications to verify. Something like this. I'd like to verify the following trigonometric equation. 1 plus sine of 2x over cosine of 2x equaling cosine x plus sine x over the difference, cosine x minus sine of x. All right, so I want to verify that these two are indeed equal. And when we first were introduced to verifying trigonometric identities, it may have been kind of rough that first step on what should I do first, like should I use this identity or that one. But in tonight's homework, or any questions that deal with a double angle, these questions are almost screaming or whispering for you to work with me. This is saying, I've got a sine double angle, you might as well apply that identity that is the sine double angle. Similarly here, now cosine does have 3 versions, but this is the double angle, so I think I'm going to apply one of the cosine double angle identities. All right, so I'm going to do that. I'm going to apply a sine double angle identity, and I'm going to apply a cosine double angle identity. So up top, I've got my 1 plus, but I'm rewriting sine double angle as 2 sine x cosine x. Down below, I've got 3 options to work with. I've got cosine squared and sine squared. I've got only sines, and I've got only cosines. So I'm going to kind of look to the right-hand side as my muse or where to go. Well, I see cosine and sine. So I think I'm just going to use the main one, cosine squared minus sine squared. So I just kind of look to the right. If I only had sines, I may use the only sine version, but I see both. So I'm going to replace this with cosine squared minus sine squared of x. I'm going to say this is equal to the right-hand side. This is just notation to, I'm not touching the right-hand side. I'm just going to recopy it down. Okay. Whew. What to do next? Well, when I look at the denominator, I see now a difference of 2 perfect squares. So I think I want to factor the denominator using the difference of 2 squares. And in fact, I'm looking at the factors right there. So that's very convenient. So I'm going to factor the denominator. Using the difference of 2 squares. Cosine squared minus sine squared can be factored into cosine minus sine and cosine plus sine. All right. Now, when I look to the right-hand side, I see that I have the cosine minus sine, but I'm kind of wanting this cosine plus sine to go away. Well, I could make it go away if I had a common factor up top that I could reduce to 1. Ooh, whew. All right, this may take some trouble seeing the first few times, but I'm going to show you one way to manipulate the numerator so that I can factor it. So I'm going to take this 1, and I'm going to turn it into, using the regular Pythag ID, sine squared plus cosine squared. Let's do that. I'm going to introduce some sines and cosines. I'm going to call 1. That 1 I'm going to call cosine squared x plus sine squared x. And what allowed me to do that for my justifications off to the right is I just used a Pythag ID. All right. Now, in my next step, I'm just going to rearrange these 3 terms. This is just a trinomial, a plus b plus c. I can rewrite that however I want to. And in fact, I'm going to put the cosines first and the sine squared last. So I'm just going to rearrange my numerator. Some students may already see the factors. I'm just going to line it up to help the rest of us who can't quite see it yet. And I'm about to lose the right-hand side, so I'm going to just recopy it here so I know where I'm going. All right, I claim in this, when I'm looking at the numerator, you should maybe be able to see a pattern you've seen before. I have a perfect square on the front and on the end, and then the middle term happens to be twice their product, so a single cosine and a single sine. That shape, we call that perfect square trinomial, and it factors beautifully. So I'm going to factor the numerator using the fact that it's a perfect square trinomial. But just any trinomial should factor to the product of two binomials. And so then, like always, with the trial and error method, you can just ask yourself, those first two terms, when I multiply them together, they should give me cosine squared. So I think cosine and cosine should do that. Similarly, the last two terms need to multiply and give me sine squared, sine and sine. The signs are the same, they're both positive. Now that's, I'm just going to make sure that works. Foiling it out, or massive distribution. Cosine times cosine is cosine squared. Cosine times sine is a cosine sine, plus another cosine sine is 2, plus sine squared. Perfect. So I factored the numerator. It just happens to be the perfect square trinomial. And I'm just going to recopy the rest of this verification. Now I see that the sum factor, they're like, everything's being multiplied together here, so I can simply reduce. Those will divide to 1, a positive 1. So I'm left with, on the left, cosine x plus sine of x over cosine of x minus sine of x, and that's equal to what we started with. And my little black box to say I'm done. All right, the double angle IDs, they can also help us with cute little graphs. So I'm not going to get too formal with my graph, but something like this. If I said, I just want to see a sketch, or you to graph the function, oh, I don't know, something like 4 sine x cosine x. So some function out there, 4 sine cosine. And I know how to graph sine, I know how to graph cosine. I was never taught how to graph the product of the two, and I do not want to do like a t-chart. That sounds horrible. So hopefully I'm kind of recognizing if that were not a 4 but a 2, then I would have a double angle. So I can show that step. I can rewrite 4 as 2 times 2. Yeah, so 2 times 2 sine x cosine x is 4 sine x cosine x. What I've got inside the parentheses is simply sine's double angle. I'm going to replace that. Oh yeah, now this is just a regular sine graph with 2 transformations. I've got a b, or a horizontal dilation of 2, which means I'm going to go twice as fast, or I'm going to scale those x values by 1/2. Or another way to think about it is the period change. Sine normally has a period of 2 pi, but we're speeding it up. So now the period is just 1 pi. And the 2 on the outside, my A, that's just basically the amplitude. So the from a 0 position is going to go up to 2. And just quick sketch. Sine starts at 0, sine of 0, 0, and it has a normal sine wave. I'm going to draw that real quick. This is what sine shape should look like. Normally we're done at 2 pi, but because of the period change, this is now over by the time we get to 1 pi. Normally sine has an amplitude of 1, but we're now going up to 2, so this has an amplitude of 2. And there we go, I'm basically done. I could throw in some more values, but there is 4 sine x cosine x. It looks a lot like sine. It has an amplitude of 2 and a period of pi. See you next time.